Good afternoon, everybody, and welcome to the 11th of 18 distinguished lectures on the big idea of sustainable development, business, and community. I'm Tom Gladwin, the director of the Frederick A. and Barbara M. Erb Environmental Institute here at the University of Michigan. Those of you who are loyal followers of this series know that it has been designed to raise awareness, to boost literacy, to re-examine values, and to hopefully inspire visions of an American future that can be environmentally sound and simultaneously socially fair and economically prosperous. This series is affiliated as a Journey to Detroit event leading up to the National Town Meeting for a Sustainable America being convened by the President's Council for Sustainable Development. The series here is sponsored by the University of Michigan's Business School, School of Natural Resources and Environment, College of Literature, Science, and the Arts, College of Engineering, and the Office for the Vice President of Research, with external funding provided by the Dow Chemical Company and Mr. and Mrs. Fred Erb. As usual, because this is broadcast on University of Michigan Television and the Community Television Network, the question and answer process today will be done via 3x5 cards that you can fill in your question, and they'll be brought down to be addressed to the speaker in that fashion. A few notices about upcoming events and a few changes. Next Monday, on March 22nd, Paul Hawken, the co-author of Sustainable Capitalism, Creating the Next Industrial Revolution with Amory and Hunter Lovins. Paul will be speaking at 7 p.m. here in Hale Auditorium, not at the originally designated time of 4 p.m. 7 p.m. for Paul Hawken next Monday night. Next Friday, March 26th at 4 p.m. in this room, we will have the Native American activist Winona LaDuke speaking about sustainable Native wisdom. She was named by Time magazine as one of the country's most promising young leaders, and by Ms. Magazine in 1997 as Woman of the Year. And as many of you hopefully know, we've added a whole afternoon on biodiversity in relation to sustainable development. Here on March 29th, Monday, starting at 2 p.m., there will be a distinguished panel of people that know tropical forest intimately, and we'll be talking about the relationship of tropical biodiversity to economic globalization. It should be a very profound afternoon. All of the other speakers in the calendar are still coming at their designated times. See me if you have any questions about changes in the schedule. Now, it is my pleasure this afternoon to introduce Donella H. Meadows. Her life combines the following, and everybody make a list of this. Simultaneously, she is a systems analyst, an organic gardener, a wool sheep raiser, a dairy farmer, a syndicated journalist, an eco-village developer, a college professor of environmental studies at Dartmouth College, and many other things. An extraordinary package. The Whole Earth magazine last year said she simply represents one of the most heartful, intelligent minds in anybody's watershed, which is a wonderful honor. On the serious side, she was originally trained as a scientist with a BA in chemistry and a PhD in biophysics from Harvard University. She is an extremely prolific author, perhaps most famous and perhaps most controversial for her role in the Limits to Growth book of 1972, which sold millions of copies in 28 languages, and also its 1992 sequel, Beyond the Limits, Confronting Global Collapse, Envisioning a Sustainable Future. She began her nationally syndicated newspaper column, which is a weekly, it's called The Global Citizen, which comments on world events from a systems point of view back in 1985 and has received many awards on that. She, like many of our other speakers, have dabbled in television, and she really helped PBS develop the very famous series, the 10-part series, Race to Save the Planet, that I often use in my classrooms when I don't have a lecture prepared and so on. She is the recipient of numerous awards, a Pew Scholar in Conservation and the Environment, and a very prestigious 5-year MacArthur Fellowship. On the personal side, she's lived for 25 years on a small communal organic farm in New Hampshire, but is currently enmeshed in a new, larger eco-village project that I hope she'll be able to talk about. This is a woman who walks her talk. My pleasure, Dana Meadows.
Remember to turn this on. Can you hear me? Okay. I'd rather speak from down here so I can make systems diagrams as the spirit moves me. I'm waiting for the ring to get out. Okay. Maybe, oh, it's because this mic is on.
No, that's off.
Oh, okay.
Audiovisual problems are typical in this series.
I see. I'm going to assume they're not my problem. I've been asked to talk about systems and sustainability. And since I know the stellar lineup of people who've already spoken to you, most of whom are people who I am privileged to call my friends and colleagues over decades of trying to figure out what sustainability really means, I know that you have seen a lot, and will, with the rest of this series, seen a lot of the parts of the puzzle. You've talked about energy, you've talked about consumption, you've talked about economics, you will talk about other parts, the business part next time when Paul Hawken comes. And one of the amazing and wonderful things is that there are so many good people working at so many levels and coming from so many angles to say, how can we live good lives for everyone on this planet in a way that preserves the functioning of the planet and all the other creatures in it. Insofar as I have a role other than cheerleader and experimental farmer in this picture, I guess it's to try to see it whole, to try to see systems as a whole. That's largely because I ran in an early and impressionable part of my life into people who had some systems tools and who taught me how to use them to picture, to think, to simulate, to understand systems as a whole. And that's primarily what I'm going to talk about today. But I guess I should start by talking about sustainability. I'm sure you've heard a million definitions. I'm going to use the very strict definitions that I suppose Herman Daly has already told you, because I got them from him, I think. Oops. Do it this way. I think he articulated the three biophysical necessities of sustainability very clearly. Every renewable resource must be used at or below the rate at which it can be regenerated or can regenerate itself. That's soils, waters, forests, our renewable resource base. Every non-renewable resource, our fossil fuels, fossil waters, minerals, must be used at or below the rate at which a renewable substitute can be developed, so that when, as is inevitable, that resource is gone or so far depleted that it's too expensive to use, we can get on to a renewable, sustainable substitute. Every pollution stream must be emitted at or below the rate at which it can be absorbed or made harmless by the natural systems of the world. And then typically, I know Herman didn't explicitly put this in because it's of a different order than the biophysical rules. But it's, I'm sure, what a fourth condition that he agrees with. It's one that Karl-Heinrich Robert puts as the fourth necessary system characteristic in the natural step. It's the one that has to do with the sustainability of the social system, with equity, with the fact that every human being has to be cared for and secure and feel that the distribution of the resources of the planet is fair. Not necessarily absolutely equal, but fair. Without, I have never heard any argument about the first three of these systems conditions. Anybody who knows the laws of the planet has to understand that those are the rules within which we have to design our sustainable systems. I've heard a lot of argument on the fourth one. I hear Karl-Heinrich Robert get it all the time. I don't quite myself see how one can argue with that one either. Either in order to design a world that I want to live in, or to design a world that will not self-destruct on the social level. So I'm going to consider, that's my definition I'm going to be using all through this talk of what is sustainable. And if you take that definition seriously, as I do, and you look around, you don't see a sustainable system anywhere. My own farm is not sustainable. My college is not sustainable. My town is not sustainable. My nation is not sustainable. And the human socioeconomic system on this planet is not sustainable. We are very far from meeting any of those three rules. And when I see that, I see around me everywhere unsustainable systems. As a systems person, my ears prick up, because one of the things that really attracts our attention, us systems folks, is a behavior in a complex system that occurs over and over and over again. It occurs at different scales. It occurs with different kinds of people within it. It occurs in different ecosystems. It seems not to be dependent on specific details, but it seems to override those details and be present everywhere. When that is the case, we have a systems problem. We don't have a problem of taking out one sort of people and putting in another, or taking out one technology and putting in another. We have a problem of a system that is malfunctioning and producing a result that actually no one wants. I don't know of anybody, I have never met anybody who has said to me, I really think we should wipe out the renewable resources of this planet. Or we should just use up the fossil fuels and not care what happens when they're gone. Or we should just emit pollution and so it poisons things and builds up. And nobody wants those things to happen, yet they're happening everywhere. We are all, and I think everybody understands this too, this is another very common systems characteristic, we are all producing this behavior of unsustainability. We are producing it with every action in our lives. We're producing it with the most rational and understandable and justifiable actions in our lives. We are in a system that is causing us to live in unsustainable ways. And so that, from a systems point of view, is almost irresistible to say, why? What is it? What is that system that is doing that to us? And I'm going to try, I think that's a very complex question. I've been asking it myself for 30 years. And I have some insights, and I'm going to share as many of them as I can fit into an hour today. But first I need to start with what is a system before I talk about what is the unsustainability system. This is the official textbook Systems 101 definition that every student can speak back pretty soon. It's a set of interrelated elements organized to serve any particular function or goal. It may not be the function or the goal of the people in the system or the actors in the system, but there is a large system goal which holds together the system, around which the system is organized, toward which the system is always trying to produce this result. And I colored the three most important parts of this definition. The elements are the things, the people, the factories, the physical stuff that you can count and measure and see. The interrelationships are critical. They are what we call the structure of the system. They're what hold it together. They're the rules of the game. They are the rewards and punishments, the prices, the information signals, all the things that hold the systems together. The function or goal is sometimes not at all what the system or people in it would say it is doing, but it is the result that is clearly being produced every time you see that system. So, for example, if I would say, what is the function or goal of the national economic system? There are a lot of possible goals, but the one that the system is clearly producing is growth. The one the system goes into conniptions if it doesn't appear is growth. The one that everybody keeps trying to make the system do is growth. So that's the function or the purpose or the goal of that system. Okay. That's what I mean. And by the way, I've just given you, and I better stop and point them out as I go, two very important basic points in systems thinking. The first came back when I said we all produce the result in the system that we don't want it. And we do it out of rational response to the constraints and the incentives and the punishments that the system puts on us. That's the number one really important systems insight, is that system behavior comes out of the system, its interrelationships, its goals, not the elements of the people, the actors in it. And that immediately has a profound effect on the way systems people talk, because they rarely blame people for things. They blame systems. So the fact that people act in certain perverse ways that produce results that no one wants is not usually, there are exceptions, the fault of the people in our way of thinking. They're the rational behavior of people in the system, and the question is what's wrong with the system, not what's wrong with the people in it. And secondly, the important thing out of this definition is the interrelationships. It's something that systems people just have an ear for. They spend a lot more time asking how the interrelationships go than asking who's the boss and who's on second base and things like that. Because actually you could take all the people out of the University of Michigan, put new people in, as of course happens every 4 years with regard to the students and every X years with regard to the faculty, and it's still the University of Michigan. So though people make a difference, and in a minute I'll get to how they really make a difference, acting within a system, the parts are usually interchangeable. You take out one, put in another, and the system still behaves the same way. Have you ever wondered why every president of the United States ends up sort of doing and saying the same thing with certain peculiar side characteristics? But in terms of policy, no matter which direction they come from, they kind of don't stray very far from the middle. That's because of the system around the President of the United States, which really it makes them fairly interchangeable. There are some exceptions, always exceptions. Okay. The interconnections, here, this is a better way of showing it. The importance in terms of what determines a system's behavior, where to intervene, is something I've just tried to summarize on this slide. At the top is the function or purpose of the system, the most important thing to determine its behavior. It may or may not be able to achieve its function or purpose. It may be blindsided by another system, larger system or something, but if it can, the system will do what it is set up to do. And that's its most important thing. If you really want to change a system, change that. Second are the interrelationships and connections, the structure, the feedbacks, the information flows. You can often change the behavior of a system massively just by changing the way information flows within it, or what information is available to whom. Third are the elements, which usually are a low-level way of changing a system. Fire somebody and put in somebody else in their place. Rarely, if you've not done anything here, will that make a difference. Occasionally it will, because actually you could put in a person or a technology or machine or something that will, in fact, go up and change one of these. Then elements make a difference. Otherwise, they don't. All of this produces the behavior of the system, which is its behavior, its general tendency over time. And if you freeze the system at any one point, it's doing something which is an event. This is what we see in the news at night. It's sort of one snippet of the behavior of a system. And one of the problems with the news at night is it focuses on events. Or at the most, it gets up to elements and characters and personalities and things. It gives us virtually no understanding of the long-term behavior of systems or why they're doing what they're doing. Okay, that's another set of big systems lore here, which you believe more when I show you a real system, which I'm about to do. But let me back off a minute and say something else that comes naturally with the systems territory. There's a lot of systems sayings, and I'm sure you've heard them. You know, everything is connected to everything else. The whole adds up to more than the sum of the parts. Systems is the science of complexity. It's almost the exact opposite of that which I was trained in, which was science reductionism, which is learning about something by taking it apart and studying its pieces, which is a very legitimate way of learning about something. But there is another way, which is putting the pieces together and seeing how the whole interacts. That's holism as opposed to reductionism. That's the real contribution of systems theory. To a systems thinker, it is just crazy to talk about trade-offs between the environment and the economy. It's just not even a thinkable thing, because the environment and the economy are so clearly one integrated system. And that just, it's surprising once you really get into systems how often you hear people talking about trading off one part of a system with another when you see very clearly that there's an assumed reductionism, separation between parts of the system that just aren't so in the real world. It causes some communication problems, actually, because you don't understand why people are even worrying about how to make the economy thrive independent of the environment. It's just not even a fruitful question to ask. Okay, there's so much cool stuff about systems. I could go on for hours, and I'm not going to do that. And particularly systems with relation to this very perverse behavior called unsustainability, called a system undermining its own means of support. I mean, it's a crazy thing for systems to do. I'm going to try to focus on that. And I'm going to use, as an example, this is also going to show you kind of what a systems analysis looks like. A very, very simple system, but it's one that is probably demonstrating unsustainability on this planet more clearly and unarguably than any other. And that's the system of fisheries. And I'm going to show you that partly because it's a very important problem in its own right, and also because I think it's the clearest harbinger we have of what's ahead of us in other systems. And also, I think it begins to indicate to us how to fix these systems, how to make them so they are not unsustainable. So, that's a system. And I'm going to explain this to you so you will understand it completely in 5 minutes. And this is an extremely simple representation, which can be computerized, of a fishery system. It is so simple that you will immediately see complexities that could be added to it, and a real fisheries model would have a lot more complexity than this. The virtue of this one is that I can explain it in 5 minutes, and everybody in this room will understand it. And there's another systems lesson here about simplicity. Very often when we model complex systems, and there have been a lot of real fisheries models made, we get about 90% of the insights from the first 10% of the modeling. And I think that this is an example of, this is only about 10% of a real fisheries model, but I think it's already going to give us some interesting insights just in this short time here. So, remember, we have elements, we have interrelationships, and we have goals or purposes or functions. The elements in this system, the real physical things, are the fish and the fishing boats. The square means that it's a stock of fish. It's a population of fish out in the ocean, okay? This arrow means that the fish are laying eggs and raising new fish and regenerating themselves. And this arrow means that they are being harvested, and I should put in another arrow saying they're dying of natural causes, but we're going to assume the fishery is going to catch them before they get to that point. The boats is another stock, physical stock. You could go into the system and count them at any time. That's what those squares mean. They're things you could go count, look at, accumulate in the system. They are built up through the investment in new boats. People spend money and build boats, and they depreciate over time because they wear out. And that's the elements in this system, and it's really simple. Just one kind of fish, just one kind of boat, and so on. The red arrows are all of the interconnections, the information that connects this system together. And so what this little silly fish model assumes is, first of all, the more fish you have, the more fish we can regenerate. Okay? And that's a very simple population model. And we're going to assume that the regeneration rate, the rate at which fish can successfully reproduce, depends on how many fish are already there. Obviously, if there are no fish, there's not going to be any fish regeneration. If the fish are way up at their carrying capacity of the ocean, the food chain, and so on, there's not going to be any net regeneration. Okay, so these fish will breed themselves up to a carrying capacity and then hold themselves at that point. Obviously, fish will be born and die, but on net, it will hold itself at that point. That's, by the way, the goal of the fish. And so I put that in blue. The fish are trying to regenerate, trying to populate their habitat. And they'll do all they can to get themselves up there. I'll tell you more about the regeneration rate in a minute because there's an important assumption in there, a numerical assumption. I'm not going to get to the numbers for a minute. The fish are harvested depending on the number of fishing boats and the catch per boat. The catch per boat depends on how many fish are there. If there are fewer fish, it's going to be harder. Each boat's going to pull in less at any given time. So that's why that arrow is there. Leave this one out for a minute. I'm going to leave the price out for the short term. The price times the catch gives the profit of the boat. And if the profit is positive, and if more boats are wanted and needed, it goes into investment in more boats. Okay? I'm assuming, and the boats wear out at a certain lifetime, which I forget, but 20 years. And I'm assuming that all else equal, the fishermen would like their fleet to grow at about 10% per year. They may not be able to achieve that, depends on the profit, whether they have enough to invest. But if they have enough, they'll invest that. They won't invest more than that if they have more profit. They will invest less if they, you can see it's a simple model. But there it is. Two important assumptions which are going to lead up to another important systems lesson about nonlinearities. And those are my assumption about how fast the fish regenerate depending on how many are there, and my assumption about how many fish can be caught depending on how many are there. And those are shown by two nonlinear curves, which are here. Very important. This is the regeneration rate depending on the number of fish. If there are 0 fish, it's 0. If they're at the carrying capacity, it's 0. So there has to be some sort of shape like this. It doesn't have to be symmetrical. We can change it, but it's assuming that in the middle, when the carrying capacity is only about half occupied, these fish have a better probability of living and reproducing because there's unoccupied space, there's uneaten food or whatever. And so there's a peak, and it falls down on either side to 0. Okay? This is a totally made-up set of numbers. Real fish, we'd have to go in and do a lot of research to figure out that curve. The second is the relationship between the fish and the catch. And this is assuming if there are no fish, there's no catch. If there are a lot of fish, there's a lot of catch, and that there's some kind of declining curve, which we've made nonlinear here. So as the fish population goes down, it gets harder and harder to catch the fish, catch fewer and fewer. Clear? Okay, that's it. What's going to happen if we simulate the system? If the system, what we do actually to run it is we start with a certain number of fish and a certain number of boats, and we set up those relationships and we turn it loose and it just simulates itself. So if we start with only a few boats and a whole lot of fish, what's going to happen? It's really fun to figure this out. Try to figure it out before the computer does. It's very humbling, usually. This is what happens, given the numbers and the relationships I just showed you. The purple is the fish, starts with a lot, comes down a little bit and levels off. The red is the boats, grows up quite nicely on that 10% growth curve and gets up to a sustainable level, and it levels